Hi. I'm going to be talking about biogenic methane, more sinned against than sinner. And after you've heard me, it may be living evidence of early onset dementia, or maybe it's another way of looking at things. So what I want to do is today tell you a little bit of what has come to my thinking, having read around greenhouse gases exhaustively for the last couple of years, and to work out where are we going. We've obviously had Hiwaka, and we've had all sorts of debate in the last year, and now we have a pause. So maybe it's a time to recheck some of the dogma and some of the issues we've been going through. So what do I do here? Yeah, I've only been here 52 years, so I find this equipment. That is? Okay. So first of all, let's give us a context. Now, I don't want to be negative in any way, but just let's see where we've got to and where maybe we should be going. And if we're looking at, we've taken up the gospel according to Borlaug, who came in after the First World War and said, we're going to produce more food by adopting different approaches. The first thing we do, we will select resistant monocultures of crops. We'll grow them, they'll be more efficient. And subsequently, the world took on the whole concept of monoculture. Whether it was animals or whether it was plants or whatever else, you can do it very efficiently. You can produce far more food, 2 or 3 times more food. And we bought into that in a big way. And obviously, we had a dairy industry which emerged as a remarkable success story. We had obviously our cultivars. We had some of the best pastoral farming in the world. We then started to produce winter crops, which is a big limiting factor in farming down south. And we grew pine trees. And we were fast moving to a world of monoculture. And then somebody came along and started talking about things like biodiversity. And no, what's appearing here is not appearing quite the same way as it's on this thing here. So anyway. So then we obviously went on, we did lots of other things. We changed the way we farmed. We went from natural organic systems to much more chemical-based systems to treat diseases, to produce new fertilizers. And we developed all these array of chemicals, which in fact were designed to control disease or whatever else. We then moved into very heavy industrial kind of farming, not necessarily in New Zealand, but globally, which brought with it other interesting issues. And then we drained the bogs and we looked at what happened when in fact we deforested. And we saw examples from overseas of deforesting in the Amazon jungle. And you can see you can very quickly change a rainforest into a desert by using fairly aggressive intervention. You can equally look at the other byproduct of deforestation or denaturation. And here we can see, obviously, the Matara. What happens to the Matara when you put a whole lot of water down it, and in fact, you don't have any kind of control systems, any plant systems along the river. So they're things that have challenged us when we look at agriculture and agriculture development. If we look really at how agriculture has evolved and the challenges it has brought with it, the reality is that up to 1960, we were in a relatively natural farm system with a little bit of fertilizer, but limited chemicals. Then we move on from there and we start to apply very sophisticated farming practices, and we very quickly changed the way farming interfaces with the environment. And we're now running the risk, and in fact, we have created a new geological period called the Anthropocene. And the Anthropocene is the geologic period after the Holocene, which was the balanced temperate phase. And this one here is the Anthropocene, which says it is the first time in history what we do affects the climate on the planet we live on. So we now are capable of changing the whole habitat on a planet. And that's why it went from Holocene to Anthropocene. So we have a challenge. And if we deny that challenge, we will do at our risk. And that's not suggesting everything is bad or you've done all sorts of bad things, but it's saying we can't continue to do what we're doing because it's not sustainable. So we have to look at other ways. We have to discover other mores to sort of move forward, or we're going to have just 2 or 3 multinationals controlling the North and South Island, and that'll be the end of us. Now, one of the biggest things we've talked about in recent years is climate and climate change. And here we see the history of how climate change and greenhouse phenomenology has developed. And back in 50 years, 60 years ago, Crutzen said there's something going on in the climate, and that is relating to some of the gases in our atmosphere. And basically at that stage, we're talking about measuring atmospheric carbon dioxide, and it's been mapped since 1960. And you can see all the way along, we've had a linear increase in temperature, which is linked to, that's the temperature on the right-hand side, and that's linked to an increase in carbon dioxide on the left-hand side. So the suggestion was there were things in the atmosphere which could directly impact on climate. The first one that was identified was carbon dioxide. The next one which was identified was methane. The next one which was identified was nitrous oxide. And it was shown that of all the gases, now remember, what's floating around the atmosphere at present is just as complex as what you were talking about earlier on in the soil. We live in a world of incredible complexity. So all these interesting things floating around atmospherically, or they're in the ground or wherever else, and these all are something we've got to take account of. So of all the gases in the atmosphere, they're the ones which are identified as greenhouse gases. If you put them in a bottle and put the bottle on a windowsill, they will absorb the heat from the sunlight. And only a small number of gases do that. So these became the target gases to study climate change. And then we saw the time at which New Zealand took on the world and won. And here we look at an OECD figure from back 10, 15 years ago, where they talked about what kind of gases we emit. Did we emit greenhouse gases in New Zealand? And here we're talking about essentially greenhouse gas production. And you can see New Zealand right at the top of the list. Of our greenhouse gases, 48% of them are due to agriculture. So saying there is a link between our industry and greenhouse gases as measured at that time. And you can see we're doing really well. You could put the All Blacks beside this and say we're good at rugby as well. And that's how it is. But the reality is we live in a different space, right? We are producing more greenhouse gases per capita relative to GDP than anybody else in the world. Now, if greenhouse gases are important, that means we should take notice. If, as Sergio said, New Zealand is unique in terms of its biosphere, we can equally say it's unique in terms of its greenhouse gases. So we better start looking at greenhouse gases and asking the question, is there a problem and can we do anything about it? And is what other people are doing overseas relevant to us here? That's really important. And then we see over time that hasn't changed. New Zealand is still at the top and Ireland is still struggling to catch up. So that's all good. But you can see still we are producing lots of greenhouse gases, and that's linked to our GDP, and it's linked to our premier status as a farming country. And you can see when we split that down the middle, half the greenhouse gases obviously here relate to agriculture, and the other half relate to climate and transport and all sorts of things. So we have clear evidence that greenhouse gases are important. So if they're important, which ones are important? And I've already talked about carbon dioxide. And obviously the ability of a particular molecule to absorb heat relates to the links between the molecules. If you've got double bonds between the molecules, that means they're strong. So it'll take a lot of energy to force them apart. So we're dealing here with the dynamics of chemistry. But we have here carbon dioxide, we have beside it nitrous oxide, we have beside it methane, which are three dominant gases which are talked about in New Zealand as greenhouse gases. We also can introduce other molecules which are very important, like water. Water essentially will absorb heat and will cause climate change, but it's part of the symptoms rather than part of the cause. Because we have increase in temperature, we then have atmospheric rivers and atmospheric lakes, and they come over us, and you see what happened if you live on the east coast of the North Island. It's been very, very bad, because obviously water has become essentially the indicator of climate changes in other places, like the equator. And then we also have molecules like ozone, which also seem to be of some relevance. So let's now consider what are these and what are they all about. first of all, let's look at methane as being one of the important greenhouse gases which we're very concerned about. And New Zealand is very concerned about. So let's look at what happens with the production of greenhouse gases involving methane. The first thing is that methane is everywhere. Every living thing that dies ends up producing molecules of methane. So methane is the end stage degradation product from biological material, which means we find it everywhere. So if we're looking for methane, it's very easy to find it. And we find it, obviously, because it's part of fossil fuels. So obviously they started out as organic material, and when we obviously burn fossil fuels, we emit methane and carbon dioxide. So fossil fuels are important. Agriculture is important, as we're talking about today. And then we have other sources of greenhouse gases which are also important. But the thing to note here is that with most of these gases which are produced, and the total amounts are a mean of 576 million tons produced per annum, you can see here that the amount produced, and also we have a system for consuming these gases, so the amount consumed and the amount produced, which is the source and essentially the sink, if they're equal, then we have no residual gas. If they're not equal, we're going to have an excess or a deficit. And here we will have an excess of greenhouse gases because we produce 576 teragrams and we consume 556. So we're left with this unhappy figure of about 18 teragrams of gas, which in fact is not being consumed and not being used within our atmosphere. And that means over time, if that continues, we're going to increase the amount of methane in the atmosphere by about 17 teragrams each year. So that's obviously a challenge. We're not in balance here. We've gone out, 20 years ago, we were in balance, but we're not in balance anymore. So now methane is building up in our atmosphere. And we, at this stage, are being accused of producing ruminants, which are producing methane excessively, and that methane is causing this imbalance in methane atmospherically. So why do we get that? Well, we get that because cows do two things. They obviously pee, and they also poo, but they also breathe. And when these animals eat the sort of conventional food that they eat, which is plant food, they have to break down the cellulose and the complex carbohydrates, and that requires they have a completely different kind of physiology than omnivores or individuals who eat mixed food. And that is they need special enzymes to break down the cellulose, the indigestible material in plant material, and that ends up, a byproduct of that is the production of methane. So ruminants produce methane as they eruct it. It's called eructation, which is, we used to call it chewing the cud. I don't know if you still call it chewing the cud, but that's what the deal is. So they produce methane. They also produce carbon dioxide. Now, carbon dioxide we put to one side because it's a bit hard to try and manage at this stage. So we're not onto carbon dioxide, but we are onto methane. And we say that if we look at the characteristics of methane, it's a short-term gas. If we can control methane levels, even if we can reduce them by 10%, that means we can start to control the increase in temperature on the planet, which is really quite exciting. So it says methane is an interesting molecule. And there's no point in you as a farmer saying it's not important. It is important. And if you don't do something about it, it's going to be at your peril. So we have to consider methane is important, and we as farmers should be taking it seriously and working out what are we going to do about it, if what we need to do about it. So that's what we get. The cow produces methane, which it belches out and farts it out the other end, and we have methane. We also have carbon dioxide. We're now focusing on methane coming from ruminants. And if we look at that, what can we say? Well, obviously, the methane coming from animals or coming into the environment can come from multiple sources. It can come from all these different biological sources, or it can come from coal gas, shale gas, petrol, oil. All these things which contain organic material, all are obviously capable of generating methane. So if we look at what's happened to methane over time, well, what we saw was from, I can't even read those, but what are we there? up to here, which is about 2005, or 2007, something like that. But anyway, what it's doing is it's going up, and then it's leveling off. And we say, wow, there's something we've done here. We're controlling methane. So you can see that the methane is flattening out here. We say we're home. Got it? We're doing something now. We're onto this. We're controlling this methane. And suddenly then it spikes and it goes back up again. It's now increasing at a faster rate than it's ever increased before. So we haven't solved methane, or we haven't done anything to reverse it. But how do we interpret the origin of that methane? Because depending on where this methane comes from, it may require a different solution. And there's two basically kind of solutions or two basic sources of methane: biogenic methane, which comes from living material, or fossil-based methane, which comes from gases, petrochemicals, and all the other things. And if you then look at the literature, you start to see a literature emerging to explain what's happening here. And obviously, this spike here now, which of increase again, we now analyze where did the consistent increase of methane come from? And the common response was, oh, it's come from two sources: agriculture and wetlands. We've had wetter periods, so we've got more wetlands, and we've obviously got the belchers, the cows and the sheep, they're doing it. So this is the cause of the increase in methane. So it's an industry problem for agriculture and the habitat and lands they live in. And then if you go to Oxford, or if you go to Harvard or Yale, you may put up your hand and say, hey guys, there's other ways to interpret the data you're looking at, and that is that it's not animals at all. So what you're trying to turn it off as it's your problem. It's not necessarily the problem of wetlands or the problem of farmers. Because if you look, and this was the argument they used, that's the same graph up top, which is basically the amount of the level of methane emitted, and you can see that you get the flattening off and the increase. Then if you look at the isotopic nature of that is what kind of nuclear material is making up that methane, what you find is there's two kinds of carbon molecules that make up methane: carbon-14 and carbon-13 and carbon-12. And the statement was, now when we look at the source of these two kinds of methane, what we find is that the lower methane comes from the natural gas. The lighter methane comes from sorry, I've got the wrong way around. The take-home message is that the real gas, the natural gas essentially goes like that because it's a lighter gas. And in fact, if it was the heavy gas, it should go that way. And in fact, it doesn't do that. But the reality is that if you look at the gas, the isotopic measurements, what you can see is that shale gas is in fact a light gas, but it was presumed to be a heavy gas. And that's where you get this effect here, because this is shale gas kicking in. So it's not animals, it's not wetlands, it's much more likely associated with rogue gases coming from the petrochemical industry, where there are millions of open ducts pumping out, some of them 1,000 tons per hour. So there's a little bit of politics going on here, but obviously so then we look and we see we've got three different kinds of gases. We've got the biogenic ones, which we're interested in, and we're interested in explaining what part of that problem do we own? Because we're quite happy to do what we own about our problem, but we're not going to carry the can for the petrochemical industry or other areas who are basically saying it's your problem. Now, obviously, measuring methane is a difficult science, but it's still, you can still get figures which mean something. So there we have the three different kinds. And what I'm saying is what we need to do is make sure that the biogenic gas we're responsible for producing, we look after it. If we look at what do we do with the gases we produce, or how can we get rid of them? Well, if we look at the case of methane and biogenic gases, their advantage is that when we produce methane, that makes it a source. When it has a life of biologic activity, that obviously then gives us an outcome, which is a sink. As I said, if the sink and the source are the same, you don't have any increase. So here we're saying there are agencies nature has to control methane when it's produced in the soil or in plants. And that is, we can use microorganisms to break it down. We can use methane, we can use methanotrophs, which consume methane, or we can look at methanogens, which produce methane. And if we look at wetlands, that's exactly what we find. What we find in the aerobic or oxygen-rich area of the vent, we will find methanotrophs, and they're busy chewing up methane. So a normally healthy wetlands should be in neutral. They should have a balance between methanotrophs and methanogens. And that's what happens naturally, unless we stuff it up by draining all the wetlands and doing other things. And then we have another system, which is what I want to talk about, if I've got time, is the really important medium for controlling greenhouse gases, methane most especially. And that is what is called the hydroxyl radical. And the hydroxyl radical is a molecule whose function has only been discovered relatively recently, but basically it's essentially a radical or a charged molecule called with hydrogen and oxygen in it, called hydroxyl, and it has the ability to interact with a whole range of different biological material to neutralize it and remove it. So basically, the hydroxyl radicals are the detergent or cleansing system of the planet. And these hydroxyl molecules neutralize every kind of gaseous thing you imagine. So all the poisonous gases, all these things are all neutralized by hydroxyl. And hydroxyl interacts with carbon monoxide. It interacts with carbon monoxide with methane, and a whole range of different molecules, and it's important. And if we now look at what makes the methane from animals different from the methane from industry and from petrochemicals, what makes it different is when the animal eructs methane, it does it in an environment which has all the molecules necessary to control that. So when it belches out some methane, there is in the environment a number of different radicals, all which combine to essentially cleanse the atmosphere. So what you've got here is, these are called voluble organic compounds. And voluble organic compounds are the molecules produced in nature which give flavor and odor to things. The classic is the smell of new mown grass. So when we cut our grass, what do? We damage or we wound the plants, and the plant sends out a defense mechanism, which is called a terpene. And those terpenes then cause interaction with other molecules, and you end up producing hydroxyl. So this is a way of essentially controlling what's going on in a local environment in terms of managing methane. So we have the volatile organic compounds here, which are all coming from the plants, which have I heard it the other day. I heard some vox down in Awaka. I was on a farm, and the animals came in there to this highly mixed pasture, polyculture, and as they're chomping through the pasture, you could hear them ripping the grass out. And boom, I'm thinking, wow, shit, there's VOCs all around me. It's really exciting. But that's what's happening. There's a whole consort of things going on. And that means the amount of methane that is disclosed as being emitted by animals is not correct necessarily. Because if those hydroxyl radicals are consuming a significant proportion of the methane, then we don't have X grams or kilograms of methane. We have half that, or a quarter of that, or maybe a tenth that. And we've never done that, right? All we've done is we've put a respirator on a cow and waited for 24 hours or 48 hours. And what do we see? We see an amount of methane. Then we dream on and we say, well, maybe it had a lifetime. So 12 years, 9 years, 7 years. I mean, this is like, hanging time. It's there's a lot of speculation. It's an estimate, right? And I'm saying we've got to do better than that. If we're going to say we're going to levy you for producing methane, you're an emitter, well, then you better be doing it for the right reasons. And if half your methane is essentially not been credited as being removed, so here we have what goes on at the head of the cow if they're sitting in pasture. Now, they've got to be sitting in pasture because these molecules here are all coming from living plants. They don't come from dead material. They only come from living material, which means if an animal eats some food, sits down, chews its cud, and burps, all that methane may be mopped up immediately. So we have a way of controlling the methane. And how it controls it is, it creates a chemical cascade. So it sends out these lovely molecules. We smell them as new mown grass, but the plant is doing all sorts of wonderful things. It's now producing more ozone, because ozone is the molecule needed to produce hydroxyl. So it's replenishing itself. It also produces more hydroxyl. So you've now got more hydroxyl, as you see up top. You've got more ozone, and both of these are the required molecules to produce more hydroxyl. So basically, it's now setting up, essentially replacing the bioactive molecules it needs. Now remember, a hydroxyl radical only lasts for a nanosecond. So it's produced and gone. Where was that hydroxyl? It's all, which means we can't measure it. So all those things are a bit of a challenge. Anyway, this is the take-home message. The take-home message is that there is a difference between biogenic gases produced by animals on farms and what goes on in the big world out there. In the big world out there, there's completely different kind of emissions. And this is what happens in a contaminated urban environment. You have the VOCs are working there, but they're calling into play all sorts of other rubbish, which is all condensing in the atmosphere, which is quite noxious. So we have that example of methane gone bad. We also have a reason why we can realistically look at the petrochemical industry and saying, hey, how about you guys? Because the reality is that Turkmenistan at this stage has a number of uncapped gas wells which are sending out over 1,000 tons every hour. And you say, so now it'll be interesting to hear when COPS feeds back about what they've really done about these things, but they haven't done so much so far. But you can see, and the other interesting one is India. You see, India is blue because they've got a lot of cows. A lot of cows in India, and cows produce methane. So if you are in an environment where you don't have any vegetation, you also need moisture. So what you need are living plants. If you have living plants, you have a system designed to manage methane. So, but it's a little more complicated than that, because it interacts with carbon dioxide and other molecules in the atmosphere. If you have a change in carbon monoxide, if you have a change in a massive increase in carbon monoxide, it will consume some of the hydroxyl, and there's not enough left for the methane. So there's a balance between these different consumptions. But it's all there, it's all scientific in terms of, now. And we say fracking is not a problem. I say it's a fracking problem, all right. Because if we look here, here's somebody making the coffee. You don't even have to put it in the pot. You get the water on fire coming into a container. And so this here is the methane being expelled from the water coming out of this tap from the local frack. So we have, in the last 20 years, essentially permeated the whole planet. Well, all those places where we've gone fracking or pumping a very high pressure pumping. So we've now generated essentially a replacement fuel for solus, which is gas, but it's not good gas, and it may come at a hell of a price. And we're saying we're allowing us to be blamed for that kind of outcome. I say no, we shouldn't. And I'm not suggesting that I know how many molecules of hydroxyl are needed to consume how many molecules of methane from the front of a cow, but I'm saying you're not getting the correct answer by looking at what goes into a steel respirator. Because nature is all about biological molecules interacting. And that's what's the deal here. So I'm saying, if you look at these animals here, I'll guarantee there's bugger all methane leaving that paddock. Because they're down, they're muzzling around. And equally, if you have the right kind of nutrition, where the animals are not eating all the time, but they're chewing the cud for lots of time, that's probably even better. So you want to create an environment for your animals where they've got the right kind of nutrition, but they're also sitting down, they're chewing the cud, they're doing the things normal, healthy animals should do. And that's the alternative. That's nature controlling what's going on, rather than us talking about vaccinating against methane or all the other things we said we're going to do, or changing their diet so they're going to have below methane. So I'm saying there, if you farm your animals that way, you have a right to go to court and say, I'm not shedding methane. And this is the alternative. Those guys are shedding lots of methane because there's nothing living around them, only themselves. So you can see this here, because there's no living things, because the one thing a living plant does, apart from producing volatile organic compounds, is it produces moisture. And moisture is the essential molecule needed for water to essentially produce hydroxyl. Because the UV hits the water and the ozone and breaks it down, and suddenly you get magic hydroxyl. So this is really important, and the joy of the living matter is plants transpire. That means they suck water out of the ground, they transfer up through their circulatory system, and out at the stomata, they pop out the water, and that allows them to essentially control methane. There is a farm which is typical of most North American farms, and you can see if there's color, it means there is methane shedding. This essentially is a feedlot, nothing living around it, and lots of methane coming out of it. So what I'm saying in the take-home there is that if we're talking about methane in animals, it could be a problem if you're going to rear those animals in total isolation from anything else living. If you put them into the right kind of environment, where you produce essentially the sink, well, then you make it something. And I'm suggesting that really there's nothing magic we need to do about methane. And obviously I can say this now because it's the last time I'm going to be saying anything. But what I passionately believe is we need to ask questions about who has the evidence. Everybody keeps on telling me, you have no evidence. And I say the absence of evidence is not the same as the evidence of absence. You haven't proved it's not there, right? You're suggesting it's not there because I say you've no evidence. I'm saying we've never done the bloody thing. We've never checked it. So let's go out and check some of these things and find out how much truth is there. How much does natural hydroxyl consume? And what does that relate to our animals? Because it may well mean that animals living in a nice habitat on a good diet are always carbon neutral. All we've done is look at animals which are living in very extreme sort of managed conditions in feedlots. If you're in a feedlot, you're going to shed lots of methane. If you're in a fertile pasture, you may not shed any. I've gone over time, I'm sure. But what I would suggest is if we look, there are solutions for the three major greenhouse gas molecules. If we want to control carbon dioxide, what we want to do is get a bit of balance back into our production systems. Healthy soils, good carbon storage, we can do an awful lot to essentially redress this balance for carbon dioxide. Methane, we can use our hydroxyl radicals to essentially mop it up. Nitrous oxide, let's first of all consider using synthetic fertilizers in a more restricted way, and that'll give us one hand up. Water vapor, essentially, water vapor is something which we can't control until we start to control the temperature of the planet. And the way to control the temperature of the planet is have it covered in vegetation with lots of shade.